To a very small scale.
Brute force works for a very small, at a very small scale. What? Yeah, I mean, those old things at the time, they were probably like, whoa, this is the fastest computer ever. And, you know, yeah, they were like, you should have seen the computers 20 years ago. Right? I mean, it's like, for them, this was like, so, yeah, so they're running on, of course, on very, you know, on hardware of the time now. So brute force, so what's the idea? So brute force what? Brute force search of
Instructions.
in sequences of instructions, right? So you start with like, it's length 2, length 3, length 4, and you just keep on, and okay, so great, so you do that, and then what? You get all these sequences, so you enumerate all possible, I know, it sounds really crazy, right? You know, by the way, I should point out, this is a seminal paper. You know what seminal papers are, right? It's like these papers that are like, you guys are in the presence of history here. It's actually the first time that they coined this term super optimizer. At the time it seemed like a kind of crazy idea, but actually there's been a lot of work and a lot of, I mean, it's like a whole research direction of exploring these kind of things.
They got it done in 3 pages.
What?
And they got it done in 3 pages.
What?
They got it done in 3 pages.
I know. Well, they have a long appendix. But wait, so wait, hold on. What were we talking about? The key idea, but wait, we got past that. The long sequences of it, these sequences, then what do you do? What do you do when you get your sequences? By the way, this points out also that if your assembly instructions are simple, right, if you have a kind of very small set of assembly instructions, this is much more feasible. So this kind of technique works much better for RISC architectures rather than something like that has a bazillion different things. Yes?
Yeah, I was going to say, they're assuming that all their instructions will be uniform calls, and I'm not sure what are going to beat that or let their...
Right, so they're trying to find, and that's certainly not true. Right, so in this paper, there's been a lot of follow-up stuff where people, even GCC there's a version of the GCC super optimizer, although it's not used in practice, and we can actually, one of the questions we'll ask next time when we read a kind of a more recent paper is why are people not using this kind of stuff more in practice? So that's a limitation, but before, let's just get to the main idea, because we haven't finished yet. So I brute force generate all possible assembly instructions of length 1, 2, 3, 4, 5, and then what do? I check for equivalence of my original code, and they have this thing where they talk about these Boolean expressions, right? So you encode it as a Boolean expression. They kind of like basically they explode it into they express everything in terms of each bit, what it is in terms of a Boolean expression in terms of the inputs, and then they basically check for equivalence of those expressions. And of course, that sounds completely ridiculously expensive, and in fact, it is expensive. But they have this trick. And the trick is it's a very simple trick, but it's so insightful that you're like, yeah, why didn't I think of that? That's really smart. And what's the trick?
They have some input cases and they see what...
Yeah, you just run it on some cases, and most likely if they're different things, in most cases, you're going to generate random crap, right? And that random crap, you're immediately going to print it out because you're going to run it on the first test case you're going to run it on is going to use something different. And so it's interesting, and in fact, I mean, the funny thing is, I don't know if you guys read all the way to the end, but what happens at the end, so they have to...
They drop the Boolean one and they say, oh,
yeah.
we never found any issue with the problem.
Right, so they have the fast test, which eliminates things. Yeah. And once they eliminate things, they're left with a handful of things, and for those things, ideally you'd like to put the expensive test that kind of checks the equivalence. And what do they do? Like, forget it.
In practice, we haven't found this to be an issue. They didn't try.
Right. So no, but they're very honest, and that's part of why these kind of papers would be very hard to get into. I mean, there's a lot of limitations here, but part of the thing is at the time the technology for doing this kind of equivalence testing was not very good. Things have gotten a lot better. Now we're able to do for this kind of straight line code. I mean, testing equivalence is a relatively well-known and well-established. There's very well-known techniques for doing these things. And the reason why there are very well-known techniques for doing these things is because in the past 10 to 15 years, there's been a lot of work on, well, first there were SAT solvers, Okay, so people came up with a lot of very good SAT solvers, but then beyond SAT solvers, when you reason about these things, you need more than a SAT solving. You actually need to reason about bit vectors. You need to reason about various kinds of what are called theories. Or a theory of arrays, of bit vectors, and people came up with this idea of SMT solvers. Have you ever heard what an SMT solver is?
Sorry, finish.
What?
Sat modules.
I know it's totally not that. I know that's totally that's totally not that. But SMT definitely stands. I know it's like no. Sorry, I didn't mean to make out. Sorry. I mean, I didn't mean to. What I meant to say is, I really meant to say yes. It's a common misinterpretation because SMT stands for that as well, for some intelligence multi-threading.
Yeah.
But it also stands for someone else said. What is it? Someone else.
Sat modular theories.
Right, satisfiability modulo theory. So it's basically what you do. You're kind of almost doing SAT solving, where you have various kinds of theories, and actually over the last 10 to 15 years, people have built extremely good SAT and SMT solvers. And because of that, we're now able to verify those kinds of things pretty efficiently. I mean, of course, we're able to do it very well. They talk about limitations like memory and reasoning about pointers. We're actually able to do that really, really well these days. Where we got sidetracked? What? Okay. So, cool. So what else is there? So is that it? So they have this example here, which is pretty nifty. It's a little bit hard to follow. Who followed it? Yeah, you have to work at it. The point is that's the point. The point is that you wouldn't have written this.
It's unintuitive.
Yeah?
It's unintuitive.
It's totally bizarre. And actually, yeah, totally bizarre. The thing is, but I should point out, there's this kind of weird thing where, I said, oh, this works better for risk because there's less things to explore. And that's true, but on the other hand, on risk, you have much less of a chance of finding these kind of bizarre things. On x86, there's like so many different weird ways of doing things and so many instructions that you have available to you, and combining them in interesting ways that actually allows you to find sometimes really kind of interesting kind of ways of encoding certain computations in assembly. Okay, and so what else is there in this paper? Anybody else want to say something? Yes?
For instructions that's like x86 where the instructions are of different sizes or they take different clock cycles. So isn't that a better evaluation that how many clock cycles is it?
Absolutely. That's definitely. There's been many follow-up works. We'll read one of those papers. That's part of the problem. I don't know which one we should read because there's a trade-off between. There's even papers as recent as like a year ago that are actually showing really cool things, and they use much more sophisticated cost models where they actually either execute the code and time it. I mean, that's one way you could do the model. Or they use more sophisticated model where they actually associate a cost to every kind of operator. Definitely. So that's definitely kind of a limitation of this work.
They do not talk about, they talk about the exponential subspace in terms of instructions. I have a feeling that it could be true of the number of variables as well, which are instructed.
Right. I mean, so I think that they include that as part of the thing. I mean, really what happens is it's not just instructions, but also for every instruction, you can put in different variables. Right? And they have ways of putting out like combinations that don't make sense. And also there's a lot of namings that are isomorphic. Right? So basically it's like you can actually encode a particular computation using the XY registers, but you can also encode the same thing using the XZ registers, and those are kind of they're going to be exactly the same computation. So you want to kind of not explore those separately, although I don't think they actually do that. There is follow-up work that proves it that way, where you only take things that are isomorphic up to renaming. What does isomorphic mean up to renaming? It just means that
If you rename it, it's the same.
yeah, exactly. That's exactly it. Okay, so they have some. By the way, notice that the evaluation is very sparse, right? They have an appendix where they talk. Actually, did anybody look at the appendix? Yeah, it's interesting, right? They have all these examples of things in here. It's actually really cool. what they did, they have these, for example, multiplying by constants, right? So, right, because I mean, you can do a multiply, but a multiply is pretty expensive. So you can actually kind of do it out of these different kinds of adds and subtracts and all this stuff. So it's pretty interesting that they can do that. But they do many, many different things here, and they try it out. So it's interesting to see all these things, how it actually works. Anything else? Anything else to add? Yeah.
In the absolute value function, it says that the resulting code has actually more number of instructions, but it runs faster.
Yeah, I don't know how they actually. So my feeling is this is a half manual thing, right? So they actually look at all the results that pass the. So what are you? Sorry, what are you asking? How is it possible?
No, I'm asking what is the cost function if not the number of instructions? Is there some weight associated with the instructions? Like this is like branch should not be there or something?
Okay, you want. So my understanding of how this works, or how they did it, is that they just ran the search, and then they pruned out everything that failed the original test, and then they looked by hand at everything else. And they made sure that they were equivalent, and then of all those things, they picked the one that they found to be the most. And at that point, they could probably just measure them, they could look at them, and an expert can see which one runs the fastest. Because at that point, they don't even run the other tests, they just look at them by hand. And I suspect that you actually don't get that many that are equivalent. That's the point. That's kind of the insight here, is that there are very few things. There are very few ways of computing the absolute value, right? I mean, it's not like there's a bazillion different ways. There's a kind of a straightforward way, and there's going to be like some crazy ways. But how many crazy ways are there, right? It's like, yeah. Wait, you had a question?
So why did their program report an answer that is larger than the original? The answer should be the original.
They would have had to have a cost function.
No, I think so. It's a brute force approach. They probably generated the original one too, and then they went on. I mean, the point is this: they're doing a brute force.
They said their implementation that when they find the shortest one, they're guaranteed never to find another shorter one, because that is anything else is going to be longer or equivalently long. And so they print it and they terminate.
Yeah, but obviously that can't be the case if they're finding something that's bigger than the original, because they would have found the original one first.
Right. That's what he's saying.
Right. So I agree. I think what they're doing here is they're actually just running it to basically a certain number, a depth, right? Like depth of size 4. I'm speculating. Obviously, I mean that's what I think is happening. But yeah.
Also, I think another constraint that they mentioned here is they're trying to like do it without jumps, right? So the original one could have jumps, but the shortest one that they can find, like the brute force technique can find without jumps, might be longer than that.
I see. So did the original one have jumps in it?
Yeah.
Okay, so maybe that's what it is.
That's what their cost function is like. Jumps are 100 instructions maybe or something. So.
Well, actually, I think they don't generate jumps. I think that's what it is. They just don't generate jumps. So maybe that's the explanation for that, is that they just generate. So the reason why it's longer is, and they actually don't hit the original ones because the original one had jumps. They don't generate jumps. That's a very good point.
Yeah, I think they say they're only using a subset.
Yes, absolutely. And they don't. And I mean, once you generate jumps, it gets really crazy. And you can generate. Yeah, it's pretty crazy. Yeah.
It actually says excluding conditional jumps from the instruction set.
It's on right here on the thing.
Yeah, this might be faster than the classical
Wait, what?
method.
Oh, I see. Cool. Now that remains to be seen. Now the thing is, it remains to be seen whether on a modern architecture, whether this will be faster than the actual shorter sequence with jumps. But because if you have good prediction of your jumps, then maybe that it's okay. Okay, let's see. Anything else? Was this like an amazing paper? It's like really cool. I mean, you have to. It's no what? It's just.
If somebody asked me to do this, the way I would think about it, is I can't think of a much better way than brute force, immediately. And so I could say, well, I could do this, but only for really small things. And then so they wrote a paper saying, oh, we did the naive thing. We just limit ourselves.
Right, but here's the thing. The thing is, so absolutely. But sometimes the naive thing with some tweaks can actually give you really cool results, right?
It's good.
And the thing is that what's interesting is that there's like a lot of people following up on this and kind of trying it, especially because Moore's law gives you more and more computational power, and then also data centers gives you bazillion of computers, so now you can do this search because it's totally parallelizable, right? It's like embarrassingly parallel. I mean, so that's yeah. But it's yeah. I mean, basically, it kind of challenges your assumptions of how you should do things. Right? I mean, it's kind of a weird, it's like, let me generate all possible programs. Oh, here, let me compile this code by generating all possible programs and seeing which ones are equivalent. It's like, what? But I mean, it's a completely crazy idea, and it works on a small scale. Although now you can do it on bigger scales because we have better computers. Yeah.
Does this somehow lead to like the modern development of genetic algorithms where a computer program will just mutate randomly and then somehow the fastest program will win, and then it somehow seems like related.
Right. But but this thing about genetic algorithms is that they don't explore the entire search space. They actually kind of do some kind of, I mean, they randomly explore, they randomly do mutations, and then they combine things by selectivity. So they actually explore only a small portion of the search space. The kind of the insight, so to speak, here is to actually not do that. So really do brute force. I want to do everything, so I'm guaranteed to find the optimal thing, right? And that's yeah. But you're right. Actually, there's a whole bunch of actually work also on these kinds of. I mean, there's actually really crazy stuff that you can do. Actually, there's this work recently by this guy called Wes Weimer. I think it's completely unrelated. Let me just say it's unrelated to compilers per se and optimization, but they actually fix bugs by basically taking the program, the buggy program, and kind of applying some random mutations to it, and then measuring fitness by how many test cases pass, and then they combine the most fit one things, and they have ways of combining things and adding mutations, and they do this genetic algorithm that actually works. It works for if you take they actually studied real bugs, and they took a certain number of bugs, and I mean, of course, it doesn't work for all bugs because some bugs are really complicated. But for some set, maybe half the bugs they looked at, or some proportion, they were able to fix it automatically, which is actually pretty astoundingly shocking, right? It's like, oh my gosh, I can't believe it does that. But wait, okay, yes.
I was just gonna say it's kind of like giving all those monkeys typewriters and expecting to come out with Shakespeare.
Exactly, and they do. That's the whole point. It's like if you have enough monkeys. It's like if you have enough monkeys, and you're saying, I want the first word of a Shakespeare play.
I was going to stanza.
The first 2 words of a Shakespeare play. Then it's like you're right. But the point though is that it does lead to really kind of interesting things, right? And it's a very interesting research project. So okay. Any other comments? Last comment, yes.
A really extreme case would be just give me some test cases and then generate a program.
Absolutely, right. So, and okay, exactly. And you know what? That's exactly, I mean, in fact, there's a very hot area of research called program synthesis, where you are either given input-output pairs for what you want the input and output relation to be, or you're given a specification of this is what the pre and post condition should be, and then there are all kinds of algorithms for actually generating code for these kinds of things. And actually, one of the okay, wait, hold on, I'm just digressing, but it's too. I need to say this. So this way of this program synthesis kind of research direction has been around for a while, and they've been limited in large part by some. I mean, you can't generate huge programs. A lot of it is relatively small. But one place where relatively small programs are perfectly suited is in Excel. So a lot of times when you want to transform data in Excel, you want to write some kind of really small formula or something that transforms, like let's say processes, you have some strings and their phone numbers, but they're in different formats, right? Some of them have brackets around the area code, some of them have just dashes, and you want to transform them into a uniform format. And so actually program synthesis techniques have been used to basically generate programs that do these transformations by just giving examples of how this stuff works. And this is actually developed in the basically the compilers and PL community. And actually this feature is now in Excel. It's called flash fill. So it made it into a product. So this is how, we went from like crazy idea all the way to, it works in Excel. But they're totally different ideas, so I don't know how. But the point is that this shows you that sometimes really kind of out there ideas can actually have a real impact.
Even in database community, there is a study called query by example.
Exactly. So, okay. That's it for this paper. For next time, we're going to, actually for Tuesday, so wait, Tuesday is the project due on Tuesday. So I'm not going to give you anything to read for Tuesday. For Tuesday, you guys are going to do your project, right? And then for Thursday, I'll give you some reading, which is going to be another paper on super optimizers, but it's going to be a recent one. The problem with the recent ones is that some of them are really, really awesome, but they're a lot harder to read. So I have to find a trade-off between finding the right paper that's accessible, but also is kind of has really cool results. But we'll figure that out. Okay. Awesome. So now we go back to concept swap. So this is just a recap of what we saw last time. I'm just recapping what we saw last time. And to recap, I'm going to show you the versions. We wrote flow functions for concept propagation. Okay, that's the first thing that we did. So we wrote, these are the flow functions. You can look at them. They're in the slides. So these are what we came up with. We saw how for certain things you want to basically kind of reuse, your flow functions for the simpler statements for much more complex ones. We saw that in some cases you want to be super conservative, like for a function call. We saw, ifs and merge. Then we saw the lattice, and we saw how it was a weird lattice because we had top being the empty set. Top's always the most conservative answer, right? Top is the answer. Top is the answer where it's like, if I ask you to give me an answer right away without thinking about it, without your analysis doing anything, that's like, you should be able to return top. Top should always be a correct answer, right? Top should always be correct. So saying that there's no, that I know nothing about the constantness, it's always fine to say that. It's like, I gotta give up, I know nothing. And the bottom is a full set, which we've talked about how it's a little bit bizarre because in this full set you have bindings of x goes to 5, x goes to 6, x goes to 7, x goes to all possible constants. Kind of a weird thing. But we saw how it's actually essential when you start everything at bottom, it's essential that you have this bottom be this full set, because here at this merge node you're going to do intersection. So the first time this thing comes here, you have this full set here, and when you do the intersection you want to keep this thing around. Because if you started this at bottom, what would happen? If you started this at top, which is the empty set, this intersection would clobber this. Okay? That's why we start everything at bottom in optimistic iterative data point analysis. And then we particularly saw this example where when we did everything at bottom, we started here at bottom, we got our x equals 5, we got everything working out, we were super happy, and then we saw that if we set this to top when we start off, so if we start everything at top, we saw how we got nothing. We got nothing because this was top. It was the empty set, and this intersection gave us the empty set, and we got nothing. Okay, that's where we left off. You guys remember the difference here? This is very important. If we start at top, everything at top, this is an example showing you that you get a worse answer than if you start everything at bottom. Right? Yeah.
So, will it be correct to say the following? If from the top, one edge away, I have a solution, then all the solutions one edge away are the right solutions.
Wait, what?
From the top.
If you start at top.
If I start at the top and reach a solution which is like a one edge away from the top.
What does that mean? One
lattice. If you assume a lattice.
Okay.
It's one edge away from the top. So all the points in the lattice which are one edge away from the top, will they be valid solutions?
Not necessarily, but why does that even matter? I don't think that's true. I mean, certainly if you start with top is a valid solution. So basically, if you start everything at top, you just stop right away. You don't even need to go anywhere. You're just like, okay, I'm done. You don't get a very precise answer. In fact, you get a useless answer, right? So that's why from top you want to kind of basically you start at top, it's the worst answer possible, but it's correct. And then you basically try to get things better, little by little. But I didn't understand why this was important, that you're one edge away from the top.
Like we start at the top, and sometimes in these cases we might end up with an answer which is like not really empty.
Yeah.
Yeah. And if I see that in terms of lattice, it will be a point on the lattice.
Sure.
And we can also say that it is like 1 or 2 edges away from the from the top.
Sure.
So I was just wondering if all the points which are 1 or 2 edges away from the top would be right answers as well.
Not necessarily. I mean, you can be one edge away from the top and be a totally wrong answer. In fact, here, I mean, you may have a program where nothing's a constant, right? So just to give you an example, I mean, in our previous, if I have a loop where x is incremented by 1 every time, at the end of that loop, x should not be a constant because I don't know anything about x. It's just going to be some value. So, top is the empty set, and x arrow 1 is one edge away from top, right? It's just immediately below that, and that's incorrect. So in fact, it doesn't always hold that. If you're one edge away from top, you're going to be a correct answer. I mean, it could be that in a lot of cases it is, but there's no requirement at all.
No, if I already know that there is an answer which is 1 edge away, could other answers which are 1 edge away be valid as well?
Maybe, I don't know. Maybe let's take that offline. I'm not quite understanding. But maybe you can ask me after lecture, we can talk about it a little more. So let's see. Any other questions? Let's go back to our lattice. But this is an awful lattice. Well, it's not awful. It's a little bit weird. It's a weird lattice. Why is it bad? What's weird about it? You guys remember termination? What do we say about termination? We wanted the flow functions to be monotonic, and then we also wanted the lattice to be finite height. So this lattice is I mean, if you assume this is a set of all integers, and this lattice is not only infinite, but it's also infinite height. I mean, it's just like you can just keep on. And it's really even if this were constant, if this, for example, let's say we only limit ourselves to 64-bit integers, it's still like a massive lattice. And it's very weird because a lot of these points in the lattice are kind of inconsistent. They're very weird points, right? So, for example, if I have actually, hold on. So, if I have, for example, let's say we only have one variable. Let's talk about just one variable. Okay, so I'm just going to have one variable. Instead of doing these, this x arrow 5 and x arrow 6, I'm just going to remove, I'll talk about x because it's going to be one variable. I'm just going to put 5, 6. Right? So this is just the set of constants that I'm computing for that one variable that I'm talking about. Right? So in my lattice, I'm going to have the set 5, 6. I'm also going to have the set 5. I'm also going to have the empty set. I'm also going to have the set 6. I'm also going to have the set 7. I'm also going to have the set 5, 6, 7. I'm going to also have like 5, 6, 7, 8. I'm going to have like all these different things here. And then eventually at the bottom I'll have the set of all possible constants. Right? So what is this? What does this represent? What does this mean if I compute this information? So it really means that x is 5 and x is 6, which is inconsistent. It's kind of a weird thing. Sometimes it almost means like your code is unreachable. And in fact, x is 5 and x is 6 is kind of the same thing as x is 5 and x is 6 and x is 7. They're both inconsistent. They're both equally weird. So in some sense, why do I need to have all these different sets, like 5, 6, 5, 6, 7? As soon as I have more than 2 elements in the set, it's this kind of weird, inconsistent set, right? So the is that we can take all of these things and clobber them together into one element in the lattice. Okay? So we can take all of these things, and the only things we're left with is this big clobbered thing, which we'll call bottom now, and then singleton sets. Does that make sense? Because those are the only things we care about. We care about the empty set, because the empty set tells us when we don't have a constant, so we can't do the optimization. We care about the singleton sets, because that tells us when we can do the optimization. And we care about bottom, because bottom represents this kind of optimistic, super duper precise information that basically it's almost like I have all possible constants all at once, where that my code is unreachable. There's multiple ways of interpreting bottom. But basically bottom is kind of the super duper precise information. And that's all I really need. And so then the lattice looks like this. Basically I have top, you have bottom, which represents all possible constants, which is kind of a weird thing. And then you have basically individual constants. And this is for one variable. Does that make sense? So we start everybody at bottom, which means it intuitively means all possible constants, which is kind of a weird thing, but it represents the set of all constants. And then we basically have top and we have individual things, and whenever we do bottom meet with some constant 5, we basically get 5. And the reason why that is because this represents kind of the set of all possible constants, and this represents intersection of things. So intersecting the set of all possible constants with 5 gives me 5. Okay, does this make sense? That's all we need. Right? That's all we need. We need bottom, the constants, and top.
So now we can have infinite lattice. So now we can have infinite lattice.
So now notice that this lattice is infinite, but it's finite height. In fact, it's very short. It's very short. It's not tall at all. It's just 2 steps. In 2 steps you've gone up to the top. Yeah.
It doesn't need to be infinite too, right? Because there can't be all possible constants in the program.
Absolutely. So, I mean,
this is just for mathematical convenience.
What?
Is it just for mathematical convenience?
Well,
why can't it be?
No, because in the program, like if you have 5, 6, 7, that's all the constants that are mentioned. Then
yeah, but wait a minute. So the question is, what are the set of constants you want to talk? So we can basically say all the constants that occur in the program.
Right.
But the problem is that if you, for example, have x is 5 and y is 5, and then you have x plus y, and you want to compute that that's 10, right? In our constant propagation analysis, it's able, so we may want to propagate information about constants that are not in our original program. Okay. So of course you could say, let me go and do. It's the set of all 32-bit, or 64-bit values. And actually, in reality, that's the way you implement this. You'd have a top, a bottom, and if you're in here, you would actually store a 64-bit value, whatever the value is on your computer.
You have like biggins and stuff.
What?
You have like biggins and stuff like that go over the.
Yeah.
So you have infinite integers set.
Yeah, I mean, basically, sure. Well, basically, yeah, that's true. Yeah. The point is, we don't care. It could be super. It could be infinite. I mean, it could be really low. I mean, at the end of the day, the truth is, everything's finite, right? Unless
it might be so big that we don't care.
Exactly. So at the end of the day, like even your big nums are finite because you have a finite number. There's
at a certain point,
there's RAM. I mean, RAM will limit you. Actually, the number of particles in the universe is probably the limit, really. I mean, it's like there's a limit there, so we can't go beyond that. But you're right. Sometimes it's so big that it doesn't even matter. The beauty of it here is that our lattice originally was designed in such a way that it had all these other things in it, but now we can actually make it finite. Yeah.
I guess we're at multiple variables question.
Yeah, we haven't gotten there yet. That's a great question. How do we do multiple variables? We'll get to that next slide. Are you going to ask a
Question about that.
Okay, so we'll get to that next slide. Yeah.
Last lecture we talked about like where you might have x equal x arrow 5 and x arrow 7, and that meant some kind of unreachable. Here we can't get that, correct?
No, it is. It's this. It's bottom.
Oh, so that's what you mean.
Bottom represents exactly. It represents exactly that.
Multiplicity. Okay.
Right. It represents any. But what we can't distinguish anymore is the x equals 5 and x equals 6 versus x equals 6 and x equals 7. Right? We're basically corroborating all of those. As soon as you have more than one, it's like we're assuming you have all of them. It's like we have all of them. And so that's what this bottom. And actually, in some sense, the reason why I keep on saying that is so. Let me. I mean, it's one of those things where, for example, if you have a merge here, where on this side, you have x equals 5, and here you have a conditional, branch, and it turns out that on this side you have x equals 10. So if this conditional it only goes on the true side, okay, the way you would transform that is you would basically make this thing go directly here, and you would leave this code as unreachable. And what happens is when you would analyze now, if you had an unreachable code elimination pass, it would delete this x equals 10. But supposing you don't have that yet, you haven't deleted this statement yet. It's still there, and it's fine. It's unreachable code. I mean, there's very valid programs you can write like this that have pieces of code that are never reachable. When you analyze this, notice that what will happen is we initialize everything to top. No, wait, bottom, sorry. So this will be bottom here, and because this will end up being bottom. Okay? Actually, it won't. Our analysis should actually, see, this is where our analysis is not precise. It actually is not careful. Bottom really, if you have a value of a variable that's bottom, it really means that it's actually, it doesn't quite work. It doesn't quite work. We can't encode it that way. Yeah. Actually, the way it would work is like if you have this will work. So if in that example you wouldn't be able to do it. But if you had some other piece of code that had nothing to do with x here, okay, then the fact that on one side you have bottom and on the other side you have x equals 5 basically allows you to say, well, what should I get here? I'm allowed to assume that x is equal to 5, right? Because when you take x equals 5 and bottom for x, then it basically gives you 5. Right, so the information here would be 5, and then here we do 5 with bottom, which is 5. And the way to interpret this bottom here is that it's almost like this side here. The reason why I was saying it's all possible constants is that it's like a super constant. This is why. So it's not only do you know it's so okay. This is not constant. This is a constant, and you have a value. And this is even better information. It's that you can assume it's a constant, and you can pick the value of the constant you want it to be. And this example shows that. You have an x equal 10 here. You have some unreachable code here that doesn't affect x. So on this side, you have bottom for x. On this side, you have 5. And really what it says is you could just assume that on the other side, you would just get 5 if you ever come through there. You can just pick, it's like you just are allowed to pick whatever constant you want it to be. Because it will never come through there. So you're allowed to pick. So that's why sometimes you can think of this as being a super constant. Not only is it constant, but you can pick the constant that you want it to be to make your results go well. Yes?
How do we represent unreachable code? Because it can't be null, and it can't be any value. So how do we represent that?
So the real way to represent unreachable code is that you actually need to do an unreachable code analysis. And right? I mean, I mean, you can kind of try to include some of it in this constantness information. A lot of times when you have bottom for all your variables, then it probably means that you're unreachable. Right? I mean, if all your variables are set to bottom, it probably means that your code is unreachable.
Maybe I misunderstood. So, what was properly defined as in this?
So, I'll get back to this. So let me do the multiple variable first, and then we'll get back to this. Bottom here is just basically what we initialize everything to. I mean, basically, it's the most optimistic information I can get about my variables. Basically, for a given variable, it really tells me that I can assume this variable is any constant I want. Right? That's what it means. It means that if I ever get to a point where x is mapped to bottom, and that's the information I get at the fixed point, it means that I can assume x has any value. Whereas here, if I'm at top, I can't assume anything about x. I can't assume it has a value 5 or 3 or anything. Here, I can assume it has a value 0. And here, I can assume it has, any value whatsoever.
Any value is any reasonable value, right?
Yeah, any reasonable value. So for example, if I have x times 5, and x is bottom, right? I mean, I can basically, for example, say, well, you know what? It makes it convenient for me that if x is 0 here, so I'll just make this 0, for example.
How do we compare unreasonable values?
Well, there's no, I mean, it has to be an integer, right? I mean, it has to be, we're only dealing with integers for now. It has to be like a value, a value of the right type for the variable that we're talking about.
So I guess that makes sense. But like, you had an example when x equals 5 and x equals 7, it's just not possible, right? And then it would just be kind of like doing the mean.
Right. Well, let me do multiple variables, and then we can talk about unreachable code for a second. I mean, really, what happens is, in your analysis, you will very rarely finish off with bottom. If you have any bottoms in your result at the end of your analysis, it means something's really interesting going on in your code. Most likely, you have unreachable code, or you have uninitialized variables. Right? Right? Because, I mean, if you have a variable. You know what? Let me first talk about multiple variables first, and then because we're already talking about. So there's two ways to do multiple variables. One is that you do a tuple of lattices. So basically, what you do is you can have one lattice for every variable. So let's say I have 10 variables. I'm going to number my variables 0 through 9, and I'm going to basically store my information as a tuple. So for example, let me say I have 2 variables, not 10. That's much easier. So I'll have, bottom, bottom, right? I'll have basically a copy of each lattice for every variable. So this will be an example where this is my first variable, and that's my second variable. And that will be the bottom of the tuple lattice, right? The pair lattice. And then I would basically have another example. Some information is 5 bottom would be some information where I know that the first variable is 5, and I know anything about, I know that the second variable hasn't really been initialized. Or I can have this, which is that the first variable is 5, the second variable is 7. Or I can have this, which is that the first variable is 5, the second one is not constant. And I can also have basically that both variables are not constant. Okay? And so the way that you can actually define formally what this tuple lattice is, let me actually show you what it is. So basically, the bottom of the tuple lattice is you have the bottom of each one of the individual things. The top is you have the top of the individual things. The domain is a tuple. So a domain of this tuple lattice is a tuple where you have one element from each one of the domains. Join is done pairwise. Meet is done pairwise. And the height of lattice is basically the height of, you add all the heights of lattices, right? Because basically what happens is you can start, for example, at bottom, 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 right? And then you can basically make, and then I can make this one go up. This one, I can basically make the first element go up by the height, by its height. And then after I'm done with that, I'll get something where this is top, and then this is bottom, and then I can make the second one go up by one element at a time, and then I'll get top, and then bottom, and I can get the third one to go up one at a time, and finally I reach top. And so by doing, and every time you go up by just having this element go up in the lattice, you will actually get a tuple, let's say A bottom, and this tuple is going to be greater than the first one. Because comparison is also pairwise, right? So this here is greater than this one because A is greater or equal to bottom, bottom is greater or equal to bottom, and bottom is greater or equal to bottom. Okay? Any questions on this? This is, no, yeah.
Are the variables independent? Yes.
Yeah.
And they have to be.
Well, what do you mean by independent? I mean, obviously, the variables are always independent. I mean, I don't know what a... Yeah, but I mean, the variables, they're different variable names, right? So I'm talking about variables in your program that are different, like X, like I have a variable called A, and I have a variable called B, and I have a variable called C. And so I'll just kind of I'll number my variables. This is variable 0, this is variable 1, this is variable 2, and I'll just place them inside here.
Well, I was just thinking, like in the case of a block where A equals B, and then next, like C equals A or something like that.
Yeah, we'll keep information for every variable, for A, B, C, and D. And then we'll just, our information will later just map. I mean, basically we're keeping a piece of information for every variable. So it's not, I mean, there's no, it's just one piece of information for every variable. Right, so I mean, if my program has two variables, A and B, then I will store a pair where the first thing will be an element of the constant propagation lattice, and the second element will be a pair of the constant propagation lattice. Right? So, yeah. Does this tuple thing make sense, or it totally doesn't make sense? It's okay because this is not the most important one. The more important one is the map one. It's more convenient. Although the power set lattice actually works out great too. In many cases, in constant prop, it doesn't work out that great because it's this infinite lattice. We'll see that in many other cases like pointer analysis and all these things, it's not infinite at all. And so the power set lattice with the binding works out fine. But another way to do this is that basically you actually create what's called a map lattice. So basically instead of having, every time you compute, at every edge, instead of computing a tuple of information, one for each variable, we're just going to compute a map from variable name to the information for that variable. Okay? And a map is just a function. So basically we're going to store at every point in the control flow graph a function from variables to an element of the constant prop lattice. So in some sense this will look like this. It will look like a map. How do we draw a map? Maybe like this. So A goes to bottom and B goes to bottom. Right? And then when you know that A is a particular constant, this will go like this. And so given a lattice, you can do this kind of map lattice for arbitrary, it's a kind of an arbitrary lattice constructor. So basically for any lattice D and a set V, here I'm taking set V specifically because it's a set of variables in our case, we can create a map lattice, D arrow D, where basically the set is all maps from variables to an element of D. And then each one of these things is actually just works pairwise. So bottom, what's bottom? Bottom maps every variable to bottom. Right? The bottom will map everything to bottom one. Right? So this bottom here, the bottom of the map lattice is basically going to be a function which takes a variable and returns bottom one. Right? Because bottom one is my individual lattice. So in some sense, bottom one is my constant prop lattice in this case. Right, so this, you guys familiar with the notation lambda v? This is a function that takes a v and returns bottom one. So that's bottom, top, and basically each one of these things, they do things pairwise. So for example, what is this going to do? So this is how I define, if I have A, what is this? So A join B is going to be a function. And so it's going to be a function that takes a B, and what does it do? So A and B are functions, right? And this will join them together and create another function. And this join function takes a B, and what does it do? It's just going to call AB, do join 1 on it, and BB. Right, because basically A is a mapping for variables to a constant problem information, B is a mapping for variables to a constant problem information. When I do the join of these two maps, what do is, well, given a variable, I look it up in A, and then I join it with whatever it looks up in B, right? So, for example, if I want to join these two things, how do I join them? Well, I create something where I create a map where for A, I map it to what? To the join of, right, to the join of 5 and bottom. And for B, I create a map that basically joins these two things. So you basically join by variable, in some sense. And that's the formalism right here. Cool. It's not the most important thing if you didn't follow this part, but so if we go back to our example, how do we do if we're using a map? How do we write the flow function for this? This is a constant prop. So in now is not a set anymore, it's a map. So for maps, you could basically imagine that there's a map set operator where you can basically bind something. So I could basically do this, and what do I bind x to in the outgoing map? So this operation is going to take the incoming map and update x to bind it to something, and it will return it. And what should I bind it to? Yeah.
In the Y.
Absolutely. I basically look up the value that I have for y, and I look up the value I have for z, and then I apply op to those two things, and then I bind x to that. So I'm waiting for someone. Maybe you guys are too lost to kind of see the subtlety and why this doesn't quite work. Well, let's try to figure out. So this doesn't quite work. Something's kind of off here. The types are off. Yeah.
What does it do if y or z aren't in?
Yeah. So basically op is like a normal operator, like plus. So when I look up in of y, what am I going to get? I'm going to get, in my lattice, I'm going to get either bottom, or number, or top. And the same thing here. So this op here, poor op here is going to be totally confused when you pass it like bottom, bottom. It's going to be like, what am I supposed to do, right? So what's the solution to that? Yes?
We could redefine to return bottom or top depending on what.
Absolutely. Exactly. That's exactly it. Now we're not going to redefine because redefining is I'm worried about redefining because if we redefine op, then poor op here is going to be like, what about the original op? So let's not redefine op because that's going to create a lot of confusion. We're just going to define a new version of op, which we're going to say op hat. So op hat is going to be op lifted to the domain of these special values, this lattice. And the reason why I'm saying it's lifted is because op the reason why it's not intuitively, we're talking about this lifting, is because op already works on integer. And really we want to make op hat work on integer in exactly the same way, but we want to make it also handle other kinds of values. And that's what usually lifting means, that you take something and you make it, you extend it so it handles other kinds of values. So one way to do this is to basically, basically do a table. That's kind of one way to do it, right? So I have bottom. Right, so this is the case where I have, this is my first parameter. Wait, what? Let me just do it this way. So this is my first parameter. This is the second parameter. And I can either have bottom, a constant, and top. Bottom, constant, and top. That sounds like an alarm. It's not a fire alarm, right? That would be like
Sounds
much louder.
backing up.
If it is, it's far away.
Huh?
If it is, it's far away.
It's a far away. It's okay. Someone else is burning. It's not, that sounds like a big thing. That sounds like those big things are backing up, right?
It's just a car.
What?
It's just a car. It's not burning.
It's not a car. That's a car?
It's a truck.
It's a big truck backing up, right?
Yeah, I think.
It's supposed to be warning you that,
I'm going to run you over.
Exactly. Let's hope it doesn't back up into here. That'll be like,
Lecture's done.
What?
The lecture's done.
No, why? There's a front wall, yeah, sure, but if it comes to a side wall, we can still continue. Like, the projector, as long as the projector's still working.
Invite him to sit down.
What?
Invite him to sit down.
Yeah. So what do we do? What do we do with this stuff? So what do we have here? So which one? Okay, what's the easiest? Okay, so let's start filling out this table. Who wants to start with the easiest part of the table?
Constant.
What?
Constant and constant.
Oh. Okay. So
all the tops
here,
remain tops.
it's A off B. So wait, what? All the tops remain tops?
Yeah.
So right. So top. Okay. So top.
Top up, top. Didn't Dr. Seuss write that?
Well, that's certainly safe.
What could not?
Well, hold on. You're probably right. But I should find out. So hold on. So certainly top is top. I mean, that's like totally pretty clear. Top and a constant. I mean, you don't. Basically, what it is that.
If A or B are non-constants, you can't get a constant out, right?
Right. Well. Hold on a second. Hold on. Okay. Fine. Well, let's leave it. Okay. Fine. Hold on. We're good for now. Let's leave that there for now. The thing that, okay, this is the one that's so it's like you have top and bottom, so it's kind of a weird. It's confusing.
If A is not a constant, how can you get the result to be constant?
You can just choose, right? As you were saying.
Right. So the point is that if A is not, so basically, so this is where actually we go back to. Okay. Let me back up. So.
Beep, beep, beep.
What?
You're backing up.
That's true, exactly. That's exactly right. I'm not going to make the sound effect for that. But, so whenever you have, so how can we get, when we do our analysis, how can we ever have a result where a variable has bottom? At the end of our result, right? When we finish or reach with a fixed point. How can we have a variable be mapped to bottom? Right? Huh? Unreachable, right? Let's assume that we start at the top. We start all the variables at bottom. At top. Right? So we initialize everything at bottom except for the beginning of the program, where we're going to say at the beginning of the program, I'm just going to assume nothing about anything, because I'm going to initialize all variables at the top of the program at the top. So now it's like the only way you can get bottom is if something's unreachable. So now, if I have this, which basically is I mean, yeah, so now it's like, why can I not, I mean, if I have Z being bottom, doesn't that mean that this code is just unreachable, so I should just set X to bottom? Because top is safe, and it's so unlikely that you're going to get like additional optimization opportunities from this one corner case, that it's just like, you just might as well put up. Because you'll have a separate reachability analysis.
Right.
Right. Right.
So run that first.
By the way, reachability analysis, you can also implement using a data flow analysis framework. You just have two, your lattice is super simple. There's top and bottom. And that's it. I mean, it's like basically one bit. And basically bottom means unreachable. Okay, which is basically completely, bottom means unreachable, and top means reachable. And basically the way you can actually do this is you initialize all your edges of the control flow graph to bottom, except for the beginning edge, which you know is reachable, right? So you set that one to top because that's reachable. And then what do the flow functions do? All they do is they literally just take whatever's on the input and propagate it to the output. Right? And then it's like, isn't this cool? I mean, it's like now you just run your framework. And it's just going to compute these top and bottom everywhere. And at the end of the day, everything that's labeled with top means it's reachable, everything that's labeled with bottom means it's unreachable. So even that's data flow analysis. Isn't that cool? That's cool. Like, you guys should be like, wow, this is so cool. Wow. Exactly. Wow. Wow, this is so cool.
We're stunned.
Okay, so wait, this is all top. What do we do here? What do we do here? Wait, this is confusing. Wait, can I put this to bottom? How about I do that at the bottom? But these ones are confusing too, right?
Constant? Well, you're saying we could do unreachable.
Let me say, if you could put, I was arguing before that you could put bottom here because of my crazy argument of like this and that. But then I was like, you know what? We could just run a reachability analysis first with our beautiful framework. We just do top, bottom, simple lattice. Run that first, kill all the dead code, and then we don't have to worry about what exactly to put here. Basically, if it's okay. Well, yeah. Wait, what?
I said well.
Well or wow?
I guess my counter argument here is that if we've already taken out unreachable code, we still want to maintain the bottom then, right? Because even though top may be technically correct, because it's always correct, what if on a later iteration we will improve it? In which case here we can't improve it because top is a fixed point.
Right, so but what would you put here? Bottom?
Yeah. Is that incorrect?
Yeah, so the truth is it's a little bit weird, right? I mean, it's kind of a little bit weird because it's weird because this is a constant. Let me give an example, right? So if you actually think about, let's think about A as being 5.
But if
And then wait, let me just do this. So A star. No, so not 5. I'll put 0 here. And then what is this? This is bottom, right? So bottom is a set of all possible constants, right? If you actually run this, if you think about the result of actually running this, it will always give you one number, which is 0, right? And what you're saying is that actually it gives you a set of all possible things. I don't know. I mean, I'm worried a little bit. It requires, yeah. I should point out that let me just say, correctness, so this actually it boils down to correctness. You can actually go down the techniques for actually proving all these things correct, making sure that everything's perfectly fine, and actually proving that actually the semantics you give, so basically all of these things have a particular semantics. This means that it's all possible constants. But because this is right. I mean, this is what bottom means. You're saying that I can later on when I get this thing. You're saying this is bottom. Later on, I can assume it's any constant. When in fact it's not. It's only going to be 0, right?
So I was thinking of plus, where you could arbitrarily choose any constant to get any constant, but you're right.
Right. For plus it works, but for multiplication,
So
you got to be careful. One of the things here, correctness of all these things is actually very subtle. There's a lot of research on correctness of compilers and on making sure these things are okay. And later on in the course, we'll actually read some blog postings about the kind of craziness that happens in compilers. The bugs that really, I mean, it's just astounding the kind of bugs that you can find. In modern compilers are like totally like up to date and everything. They're like, you know, the GCC that you use every day. I mean, you can send in like 2-line programs that will just completely befuddle it and give you wrong answers.
Wow.
It's actually pretty astounding.
So,
and this is why, because it's very subtle. Do you realize the amount of thinking that we've been doing? I know you guys are like, oh my gosh, I'm so bored of this. Come on, next slide. But the point is that we've been talking about this one slide for this one operation, for this one flow function on this one analysis for like 10 minutes, when in fact in a compiler you have like many passes, many optimizations, many more statements in this craziness, right? It's really, really subtle to get the correctness of these things to work out. Yes?
I was just going to ask, do they do like modern compilers? I mean, will they say, oh, for certain ops we will do different things? Like here, if it's a multiply, will they add like 0 as one of the points in the lattice and say, don't treat it as a...
not for this. Not for vanilla constant top. I mean, that's not where you're gonna. Yeah, I mean, that's not gonna be. No, I mean, that's not where they're gonna put a lot of their effort. I mean, the thing that matters there is just kind of generating good assembly code, getting aliasing right, basically using the properties of the machine to actually produce correct things, and also just basically not doing, really cleaning up after all of the messes that it puts in.
So actually, for example, like 0 mult will be a separate pass.
What?
So anything like the 0 multiply will be a separate pass that.
Yeah, and oh, you mean the 0 multiply? Yeah, these are called people optimizations. They're people because you don't need any data flow analysis. Right? They're just kind of really small little things that are properties of the things, and there's many, many different kinds of these people optimizations, where you transform left shift into multiplies into left shift. There's many, many, many different versions of these things, and actually even at the very low level, you can have assembly level people optimizations. Yeah.
So the topic when we say that we don't know anything, right? That's conservative.
Wait, yeah.
So why is it not that A and bottom that we don't just go back to conservative and put top instead of bottom, because then we won't have a problem.
Wait, hold on. Just to be clear, when we say top, it's not that we don't know anything. We actually know that it's not constant. We've given up on it, right? There's very different things, right? It's like we know that it's not constant. Like we've declared it as this variable varies over the execution of the program. I can't declare it to be constant.
I think this is a good...
Okay, so what's the example that you're talking about?
Well, just like a variable and bottom. Seems like a good time to say, uh-oh, we don't know if it's constant.
A and bottom. So you're saying, yeah, absolutely. So this should be, this is what I was arguing before, is that you should be safe here. I was doing a really crazy argument to say, I think you can actually put bottom here, because of that unreachability argument that I made, and if you didn't follow that, that's fine, because then I didn't convince you enough, but the point is, what I was saying is, that's a very convoluted argument, I think it's right, but it doesn't matter, because we'll run unreachable code elimination in a separate pass, and so then we can just put top here. Okay. So the general approach to domain design is that basically you can have very simple lattices like top, bottom, Boolean lattice, like top, bottom. Okay. We can have power set lattices. We can have the kind of constant prop lattice where you have top, bottom, and a whole bunch of comparable lattices. Actually, sorry, the 2-point lattice is top, bottom. Boolean logic is basically where you have at every point of the lattice is a predicate. And then you can use combinators like tuples and maps to put these things together. Cool. So, we're going to stop. gonna wait? What day are we today? Today's Thursday. So that means we're gonna. Okay, so on Tuesday, you guys are all gonna get your project done, right? And then next Thursday, we're gonna. So next Tuesday, we're gonna have a lecture. Next Thursday, we're gonna have a lecture.